Okay. So yesterday we talked about physical properties and those physical type of characteristics, color, size, shape, density, magnetism, right, all of those. And so any type of physical characteristic is describing something that does not alter the composition. So like it doesn't change what it's made of. So a piece of paper, no matter the size, shape, color, it's still paper, right? But if I burn that paper, it's no longer paper, right? So physical changes involve, kind of those physical characteristics, but it's not changing chemically or altering the composition in any way, right? So today we're going to start talking about our second way to classify things, and that is with chemical properties and how reactive something is. So a chemical property is any characteristic of a substance that is observed during a reaction where the chemical composition is permanently changed. Right? And so last year we had talked about this with oxidation, with rusting, which is oxidation, and then oxidation with copper, how it turns that green color, but it has that patina. And so those were a couple examples. We also talked about like how acid rain can eat away and disintegrate some of the rock, and then weathering comes in and washes it away. It changes the rock. It didn't just make the rock smaller, it chemically altered the rock, and then it got washed away. So you can't undo that process, all right? And so what you learned last year in 8th grade science with physical and chemical weathering, we can just apply those characteristics of physical and chemical to our characteristics, properties, and changes this year. So in a chemical change, the original substance has a new chemical composition. It even might look similar or it might be really close, but if it's changed chemically at all, then it is considered a chemical change. And some of these are very obvious, and there's a few that are a little bit like, no, I think that would be a chemical change when really it's a physical, or vice versa, and we'll look at a few of those examples just to help kind of clear up any confusion. Anytime something is burnt, it's a chemical change. You can't unburn it. Anytime something rusts, you can like sandblast this, you can clean off the rust, right? You can get the rust to go away, but you can't make that rust turn back into that iron or steel. So you can clean it up, but you can't make it go back and turn into what it was originally, okay? And so again, think about that chemical weathering that we talked about last year. Anytime you are cooking, frying something, baking, you can't undo that. Okay, so chemical reactivity, the ease with which a chemical compound tends to react when it comes in contact with other compounds. And again, we're not going to get into those specifics. We know that it has to do a lot with how many electrons are in that valence area. If they're close to having a full valence, then they're going to be really reactive. If they already have a full valence, they're not going to react at all, like our noble gases. So high reactivity if it reacts quickly and easily, low reactivity if it reacts slowly and not easily. So our alkali, alkaline, and halogens would have high reactivity. Our noble gases would have low reactivity. They're already happy the way they are. Okay. So here is kind of a good little cheat sheet. So you're putting chemical changes and physical changes in those little, I think there's like, don't you have like openings in that box? Yeah, you have kind of like a white box, and you're going to put in chemical, physical. So these are changes that occur to produce new substances, if we're talking chemical. It cannot be reversed. So, like the little glow sticks that you get like at concerts, sometimes at parades, at the fair, right? The necklace is just like a weird yellowy greenish color, but if you like snap it or shake it, right, you basically release the chemicals that are in it, and then now they can combine. As they're combining, they're going through a chemical reaction and light is given off. And so those glow sticks are actually chemical reactions taking place, okay? So a lot of times, heat and light are gonna be an indication that a chemical change is taking place. Same thing with those little hand warmers, right? If you have those little packets, and when you twist them, you basically, thanks Nye, you are causing the chemicals that were separated to release, and then they combine. As they combine, they're going through a chemical reaction, and that chemical reaction produces heat. We said that that was an example of one of our exothermic, because heat is exiting that chemical reaction. And so because we understand this, we can harness that stuff, and we can make those little hand warmers. We can make the little glow sticks for fun. So understanding that a lot of times during a chemical reaction, you are releasing heat and light. So if you see that, like even like fireflies, right? When their little butts light up, that's a chemical reaction that's causing that to happen. So a lot of times if you see heat or light, that's a good sign that a chemical change is taking place, a chemical reaction is going on. Also the formation of a gas. So the old standby of vinegar and baking soda like to make a volcano erupt. The baking powder or the baking soda with the vinegar, when they combine, it starts to bubble and form a gas, right? Heat and light. We'll talk about precipitate when we get to solutions a little bit more. And again, color change a lot of times, like the leaves changing color in the fall, those are chemical reactions. Now, if you paint something, that is just considered a physical change, because what's underneath that paint is still the exact same thing. A leaf on a tree in the fall going from green to red, somebody didn't spray paint that leaf red, right? It's turning red chemically from the inside out, right? So sometimes color change can be a little bit, you have to think about it closer, like, okay, what is it really, okay? So anytime something is rusting, that's an oxidation reaction, that is a chemical change. Baking, food digesting, don't even have to think about it, like it's a chemical change. Anything that is rotting, so whether you're talking like leaves or plants, animals on the side of the road, right? We're gonna see a picture here, in a minute, of rotting, but that usually sticks with people a little bit. Leaves changing color, again, like the fireflies, chameleons, how they can change color, that's a chemical reaction. So physical changes, these are changes that do not produce a new substance, and typically they can be reversed. Sometimes it seems like it'd be really hard to reverse it, but they still can. So don't always just count on like being able to ask yourself, can I reverse it? So like if I'm making brownies, I have the brownie batter, I have eggs, I have oil, and I'm mixing them up. When I have it mixed, it's just a mixture. They have been physically combined. Now, would it be really hard for me to get the egg and the oil separated? Yeah, but technically they haven't chemically combined until I start baking them. So sometimes the idea of having things mixed versus actually like putting it in the oven and baking it, sometimes that can kind of confuse people, but think about it. The egg and the oil and the brownie mix are just stirred up and mixed together. They haven't like united yet. That uniting happens as they get baked. Okay. So tearing, cutting, right, all of those things, folding, that's just changing the size and shape. Painting, even like if you use markers, if you're using actual paint, you're spray painting, all of those are all just physical changes, because what's underneath that is still the original item, the wood, the drywall, the paper, or whatever it may be. Or even like your fingernail, right? If you paint your fingernails, it's still your nail underneath that, it's just you put paint over it. Okay, boiling, freezing, and melting. Those are all describing phase changes. Any type of phase change is automatically a physical change. And I had somebody 7th period, they were like, well, if you boil something and it goes from a liquid to a gas, how do we know it's not just a chemical reaction happening, causing it to like turn into a gas, like you see a gas form, like when you put the baking soda and the vinegar together. And the reason why is if you would capture that gas, that steam, and cool it off, it would drip down and turn back into a liquid. If you catch the gas from the chemical reaction of baking soda and vinegar, it's not gonna go back to baking soda and vinegar, right? And so that's kind of the difference there. But anything that is talking about going from a solid to a liquid to a gas, or a gas to a liquid to a solid, any of those phase changes going between those three states of matter is always going to be talking about a physical change, right? Because you are not changing that you're dealing with those H2O, those water molecules, right? It's still H2O, it's just how tightly packed are those H2O molecules, okay? So any phase change will always be physical. Phase change, physical. They both start with pH, and that's how I try to tell people to remember them. pH, phase change, physical. Those go together. This I think is the hardest one, the dissolving, because think about like making like Kool-Aid. You have water, which is a liquid. You take let's say it's red fruit punch. You take fruit punch Kool-Aid, put it in the water, you stir it up. Now the water looks red, like it's a whole looking different thing, right? And so it's like, okay, that powder disappears. Now my water is totally different, has a different flavor, different smell, different color. So you're thinking, chemical change took place. Actually, it is a physical change, and I'm gonna prove this to you. I'll take I have Crystal Light, so that's what I'm gonna use, like pink Crystal Light, and we're gonna boil it, or dissolve the powder into the water. I'm gonna boil it off, and then if it was a chemical change, when the water boiled off and evaporated, it should take the powder with it. If it's all one new thing, when the water goes, the Crystal Light should go as well. So we'll see what happens. All right, but dissolving is typically one of the more challenging ones that people are like, no, I think that's a chemical change. I think that those two things, the water and the powder, have united to make something new. All right, so we'll, next week we'll take a look at that little demonstration. Okay, so first example, tearing paper. Is this going to be a physical change or a chemical, Brady?
Physical.
It's going to be physical. It's still paper, right? Boiling water, which is a phase change. Phase change for boiling water. Layla? It's going to be physical. Good. So making Kool-Aid, it is physical, even though, again, I get like, sometimes that's the most tricky one. What about these teeth?
Ooh, that looks good.
What do you think?
I think I got it.
Okay, what is it?
I'm gonna say
Physical or
it's-
chemical?
I'm gonna say it's chemical.
It is. You can't undo that. People are always like, no, what if you go get fake teeth? Well, sure, that's fine, but those aren't the original teeth. Like, you can't make those teeth go back and be the way they were before. So if this is any kind of motivation to brush your teeth, take good care of your mouth, yes.
That is.
That's gross.
You should see books on dentistry. It's disgusting.
Yeah, I think you have to be a special person to be able
My
to.
sister-in-law does freaking dentistry.
Does she? Yeah, like, is she a
Disgusting.
dental hygienist?
She tried to make me read the books, and they have worse things than that, where it's like calloused on the gums, and like
okay.
the teeth, or like all of them are gone.
Yeah.
It's disgusting.
So,
Could never.
again, the chemical, it is no longer the same tooth that it was. Like, if you just look at one tooth, you can't make that tooth go back to the way it was before, right? Obviously, they can pull it out and give them a fake tooth, fine, but that's not the same tooth. You can't make it go back. So this has been chemically altered at this point. Okay, we are actually gonna stop there. We have a bunch of videos to get to.
That's good.